Consider an m by n matrix A. We define the null space of the matrix A, which will denote NUL of A, the null space. This is going to be the solution set to the homogeneous system AX equals 0. Now, sometimes this null space is called the kernel by some people, which if you've been following along the series, then kernel's like, oh, it has something to do with linear transformations, right? Well, there is a connection between linear transformations and matrices. In fact, if we define the matrix transformation associated to A, then the kernel of said transformation would be none other than the null space of this matrix as we're defining it right here. So the null space is the solution set to the homogeneous system AX equals 0. We define the nullity of the matrix A, which we'll just call it nullity of A, is going to be the number of non-pivot columns in A. This is significant because the non-pivot columns will correspond to free variables. And we've seen before that a homogeneous system has non-trivial solutions for the free variables it has. So if we count the free variables in a system, then that essentially is telling us how big the null space, aka the solution set of the homogeneous system, is going to be. Now, in particular, the null space is going to be a subset of Fn, because it's a collection of vectors in Fn. And that's where n here is the number of columns in the matrix A right here. But we can even do better. The null space is a subspace of Fn. That's actually why we call it the null space as opposed to like the null set. We know that it's going to be a subspace of Fn here. And we could try to make an argument that the null space is just a span of vectors, which we saw in the previous example, and we'll see an example in this video as well. But it turns out we can argue that the null space is a subspace directly using the definition without any recitation of spans whatsoever. We don't need the geometric argument here. Because to be a subspace, we have to first show that the 0 vector belongs to the null space of A. And that's pretty easy to do because if you take 0 times A, that's equal to 0. And therefore, 0 is a solution to the homogeneous system AX equals 0. So that gives us the null space that contains 0, right? The second condition was if the vectors x and y belong to the null space, then we need that their sum, x plus y, also belongs to the null space. So let's suppose that x and y belong to the null space. So if x belongs to the null space, it's a solution to ax equals 0. Then y is also a solution, so we see that ay equals 0. Now consider the sum here. Well, a times x plus y, well, since this is matrix multiplication, matrix times a vector, we can distribute here, and we get ax plus ay. Well, ax equals 0, and ay equals 0, and 0 plus 0 equals 0. So this tells us that x plus y is a solution, that is, a times x plus y is equal to 0, so it's part of the null space. And the third condition to be part of the null space is that if x belongs to the null space, then we need that c, which is a scalar, cx, also belongs to the null space. So again, using the assumption that ax equals 0, pick your favorite scalar c and consider the product here. A times cx, well, you can actually factor the scalar out. So you get c times ax, but ax is equal to 0, and any scalar multiple of 0 is again 0. So cx is contained in the null space, and thus checking the three conditions, we've now determined that the null space is in fact a subspace of Fn. So I want to look at an example of a calculated null space, right? And so since the null space is the solution set of the homogeneous system, we can construct a spanning set for the null space. So we want to represent the null space as the span of some set of vectors. And this is similar to what we did before, but we're going to have that perspective in mind right here. So let's take this 3 by 4 matrix over the real numbers, and we'll find a spanning set for the null space. This is going to be basically coming down to solving the system, the linear system of equations. Now, because we're trying to solve a homogeneous linear system, normally there should be like this right-hand side 0, 0, 0. But as we've seen many times already, as you do row operations to a columns of zeros, that column of zeros will never, ever, ever change. And so I'm just going to omit it from consideration. It turns out that computing the spanning set for the null space is really the same thing as just determining whether the column vectors are linearly independent or not. It's just we go a little bit further. So I have a 1 in the pivot position, 1, 1. So I'm going to use that. We're going to get rid of the 2 below it by taking row 2 minus 2 times row 1. And getting rid of the 3 in the third row, we're going to take row 3 minus 3 times row 1. So we're going to get minus 2 minus 6 plus 6 and then minus 8 for row 2. That's going to give us a 0, negative 5, 10, and negative 5. And then for row 3, we're going to get minus 3 minus 9 plus 9 and then minus 12. 3 minus 3 is 0. Negative 2 minus 9 is negative 11. 13 plus 9 is 22. And 1 minus 12 is negative 11. That takes care of the first column. For the second column, we have a negative 5 right here. I can't help but notice that everything in the second row is actually divisible by 5. So I'm actually going to divide the second row by 5, negative 5 in fact. But I also noticed that everything in the third row is divisible by negative 11. So since I'm at it, I as well do that as well. And so dividing the second row by negative 5 and the third row by negative 11, I actually can see now that the second and third rows are now actually identical. Kind of like the Weasley twins there. We're identical. In which case, we're just going to take row 3 minus row 2. And that'll just cancel out that entirely, giving us now a row of zeros. So that then gives us a matrix which is in echelon form. We can actually identify all of the pivots in the matrix now. There's a pivot column in the first and second, which actually tells us that column 3 and column 4 have no pivots. These are going to be free variables. We're going to have, in fact, 2 free variables in this system. 2 free variables. What that tells us is that our null space is going to be spanned by a minimum of 2 independent vectors. All right, and so to help us here, we're going to finish by putting this thing in row reduced echelon form. Take row 1 minus 3 times row 2. So we're going to get minus 3, we're going to get plus 6, and then minus 3 right here. 3 minus 3 is 0, negative 3 plus 6 is 3, and 4 minus 3 is 1. So this gives us our RREF right here. And again, identifying our pivots, we see a pivot in the first column and the second column. So we're going to think of this matrix now in RREF. We're going to realize this as a linear system. So we get the equation x1 plus 3x3 plus x4 equals 0, x2 minus 2x3 plus x4 equals 0, and then 0 equals 0. We don't need that. Solving for the dependent variables, we get x1 equals negative 3x3 minus x4, and then x2 equals 2x3 minus x4. And so if we write our general solution, notice we have x1, x2, x3, x4. Using the identifications we saw earlier for the dependent variables, we get the following. The next thing we're going to do is we're going to separate this vector we see right here based upon the free variables. Notice that these positions depend on x3. So if we separate those from the x4s, we get a negative 3x3. We get a 2x3 for the second position. We just get an x3 for the third position, and then there's nothing. There's no x3s in the fourth position. We're going to do a similar thing for the next vector. Take a negative x4, take a negative x4, get a 0 this time because there's no x4 in the third position, and then x4 for the fourth position. So we separated the vector according to the x3 and x4. We just separated those entirely. And then looking at the first one, everything's divisible by x3, so we factor out the x3 and that leaves behind negative 3, 2, 1, and 0. And then looking at the second vector, we factor out the x4, and that leaves behind a negative 1, 0, 1. And so it turns out these two vectors right here then form the spanners of a plane for which the null space is actually equal to that plane. Set, say, u to the first vector, negative 3, 2, 1, 0, and v to be the second vector, negative 1, 0, 1. And then we've now seen that the null space is the span of these two vectors. And so these two vectors form a spanning set for the null space, which in this case we see is a plane.